Right. Okay, so we're gonna continue talking about hydraulic fracturing and try to bring a little bit more reality to what we have done, because so far we have been a little bit too idealistic about what a hydraulic fracture is by drawing these shapes, perfect planar fractures, all with same length, all with same height, and sometimes that's not what really happens. To tell you the truth, nobody knows what's going on really there. There have been some studies in which you do hydraulic fracturing at some point, and then you drill another wellbore that goes through some of those fractures, trying to sample and to core the fractures themselves to see if there is propan in there, how much propan. If you see like relatively fat fractures and nothing else, to see the spacing of fractures, and I think there is still a lot to learn. So I think in your time there's going to be a lot going on. Actually, very recently there was an article and several articles. This was from last year, and it summarized. You see, in November 2018, it's very recent, about how fractures really look like in the subsurface. And as I told you, I think nobody knows. I think we have a better idea about what they look like, but still it's very uncertain. And one of the principal unknowns here is if fractures branch, because we have made these drawings in which these are all perfectly planar fractures, but there is evidence that tells you that fractures actually may branch. But what are those branches? And when you have branching and when you do not have branching, that's something that still nobody knows very well. But at least we have some evidence of what they might look like. Direct, like this one, in which you really get the cores out of another well, I repeat, that is drilled next to this one, and you really get to see what's going on. So if you are interested in this topic, I strongly recommend that you read this article. And actually all this work was done here at UT. It was done by a scientist in BEG that does a lot of fracture analysis. There's going to be a second phase of this project in which they are going to do exactly the same. I'm hoping that they're going to send me some of those cores so we can do X-ray microtomography before they open them up, so we can get to see where is the propant, and if the propant, there is propant screening, there is fracture turning, branching, and all those things. This is very new, and it's also very expensive to do coring after fracturing. However, for more than 10 years or so, there has been a lot of activity on trying to image fractures with another type of technology, which is called micro-seismicity. With micro-seismicity, what you do is you have a horizontal well. So this is the heel. Here, this is the toe. And as you do some of your hydraulic fractures, you have geophones that are placed on surface, but not only on surface. Some other times you may have somewhere over here also a deep well that may be an observation well. It could be vertical, it could be lateral, but the more geophones you have closer to your completion, the better your resolution is going to be. And as you do hydraulic fracturing, you start to monitor events of micro-seismicity. What do we call micro-seismicity? We usually say that micro-seismicity is micro whenever the magnitude is more or less in the Richter scale smaller than 0. What is the magnitude of a big earthquake? 7, right? 7 very big earthquake, 8. And remember this is a logarithmic scale. So you can have negative values here. Micro-seismicity usually is in the order of -3, -4, -5, sometimes a little bit bigger, but usually smaller than magnitude 0. And again, putting all those geophones in wells and in the surface allows you to see how the rock screams as it gets fractured. And by doing locating these events with 3 or more with 3 or more sources, you start to see that closer to some of these fractures, you start to see events of microseismicity. Usually those events are close to what you would expect the fracture is, and most of those events are, what do you think? What kind of events? But what kind of failure? So I uploaded. I remember this because I uploaded the exam number 2, midterm number 2, for you to practice, and there is a question there for that we haven't talked much about the modes of failure, the 3 modes of failure in fractures. Let's do that very, very small over here. The 3 modes of failure of a solid with cohesive strength are this mode number 1, which is splitting, right? You have a fracture here and you are splitting that. I never remember which is 2 and which is 3, okay? But they are kind of the same. Both of them. This is what is called open mode fracture, and these 2 are shear. And one of them is shear by, if this is the tip, by doing something like this, where you have, this is called in-plane shear. So you will cause a shear stress here at the tip. Notice that here we are pushing and the other one we're pulling. And so this is called in-plane shear. And the other one is out-of-plane shear, in which let me see if I can get to draw this. You have a tip, and here you apply a force in this direction and here a force in that direction, and you have out of plane stress shear in this location. And if I remember correctly, this out of plane, and this is called also tearing. So our question here is, let's start by assuming that there is no, it's a continuous rock mass. Which kind of failure mode you think is producing these events of microseismicity? So would you think open mode would generate seismicity? Will it generate waves that propagate and get to the geophones? Not very likely, because when you're opening this, you're just spending work in opening this rock, and really all that energy just goes into opening the rock. There is not much energy that will go further away from the tip. However, when you have this type of failure, shear, in plane or out of plane, notice that you have sliding of one surface on top of the other, and that sliding of one surface on top of the other is what creates most of the microseismicity. So most of the microseismicity observed here in the field is actually shear. There can be a little bit of open mode, but most of it is shear. And if most of it is shear, that means that many of these planes actually, as they fail, they represent some small or big fracture that underwent shear slippage, right? Each one of these at the microscale is going to be either a pre-existing fracture or a newly created fracture in which you have shear slip, and that shear slip, as it accumulates strain energy and then it gets released quickly, generates waves, which are the waves that you measure with the geophones, and then you do triangulation and you get to see where they are. With this new data, we can start to realize that many of these events actually come further away from what you expect is the main fracture. And the hypothesis here is that all of these fractures, actually, not all of them, but some of them, they do connect to the main fracture, and they can create, if they connect, more flow paths for the fluid flow to get into the main fracture and into the formation. So one of the explanation of this possible branching is that many of these fractures are actually shear fractures. Shear fractures that connect to a big open mode fracture and then eventually get to the wellbore. And again, this is just a hypothesis, but what is real is that you do see a lot of this micro-seismicity all around the places in which hydraulic fracture is performed. So let's do a few more stages. If you were to do another one over here, let's assume that we do one that doesn't grow over there. Probably you will expect to see here same levels of micro-seismicity. And if you were to do a fracture that, or a cluster that does not propagate, probably you won't see much micro-seismicity. What do you think is going to happen if next to this well and next to a cluster there is a fault, and you start increasing the pore pressure significantly at that point? We say that because of making hydraulic fractures, we can reactivate small planes of weakness in the rock or small pre-existing fractures. Well, if you have a big fault and if your fluid gets there, very likely you are going to sometimes fracture appear to turn at these locations, and very likely here you may have some micro-seismicity around the fracture too, but probably you will have bigger events that locate closer to this fault and will reactivate also the fault with shear slip. There have been cases in which some of these injection causes seismicity which is not that micro and can get to values bigger than 0, 1, 2, 3. In Canada, I think there have been examples in which you get even to 4. And most time that is caused by reactivating neighboring faults that weren't mapped before. This is not the same as induced seismicity as the ones in Oklahoma, okay? That's another thing. That's induced seismicity because of wastewater injection. And I believe we talked about that. But this is not the same. This is micro-seismicity during hydraulic fracture. So ideally, you would expect to see that, and sometimes you see that the bigger the volume of the micro-seismicity cloud, something which is called stimulated reservoir volume, the bigger your cumulative production should be. So if this is production rate and this is cumulative production, then you will expect to see that the more you stimulate, the more you produce. And that kind of makes sense, right? And there are some places, and especially the people that sell you micro-seismicity are going to tell you, oh yeah, we know this very well. And it works like that. And it sort of makes sense. But be careful, because there are some cases in which you can have quite a bit of production with small measured seismicity, and there might be some other cases in which you have a lot of seismicity and very small production. So I believe that more or less this one makes sense, right? This trend makes sense because we're saying that we are reactivating more pre-existing fractures. Those pre-existing fractures connect with each other, go into the main hydraulic fracture, and go into the main wellbore and create this sort of fractal structure where you have very tiny fractures that go into small, relatively bigger fractures, and then into a big prop fracture, and that goes into the wellbore, and so on. So that would explain this trend. Let's try to see why we could have these two other cases. Let's start with this one first. Any guess why we could have lots of production and no microseismic activity?
The rock was already very fractured.
The rock was already fractured?
The rock with high permeability.
Okay, no, yeah, okay, that could be a good answer. If the rock already has a high permeability, then very likely it doesn't matter how much fracturing you do. But if the rock has already high permeability, you wouldn't do any fracturing to start with, right? So let's try to see in cases in which the permeability is low. What were you saying?
I was saying basically the same thing. If it already has a lot of cracks running through it, you don't need to create new ones.
Well, if it's already fractured and you do hydraulic fracturing, you get to reactivate many of these small fractures, and you will still see quite a bit of micro-seismicity. The question is, or the answer is, it's a little bit different. It's a little bit more about rock physics and about earthquake mechanics. There are two types of shear slip. One which is called seismic, and another one which is called aseismic. In the first one, if this is the amount of shear displacement, let's call it gamma, you may be at an equilibrium friction coefficient, which is somewhere over here, and then as you create the shear displacement, the friction coefficient sometimes goes up, but then after it goes up and you start mobilizing the shear displacement, it goes down. It goes down into a value lower than the dynamic friction coefficient. So let me move this up. In this case, then you will go into a case in which your static friction coefficient is higher than your dynamic friction coefficient. So that means that as you're sliding, the friction coefficient is actually smaller. And because it was smaller than before, usually this accumulates a lot of strain, and when it sleeps, it releases it very quickly. So this will be the case of seismic shear slip. And on the other hand, there are some other types of materials and rocks in which you see the opposite. You may be at some initial equilibrium, and as you start causing a displacement, this one could reach a maximum and probably go into another value, which is going to be the dynamic friction coefficient. In these cases, you will tend to have a aseismic shear slip, because basically now you need more stress on what you had before in order to produce a shear slip. So while this will be more like an unstable process, you guys remember like these drawings, so this will be unstable because you go to the top and then you fall a lot. This is the ball. This will be more like a stable process because you move here the ball, but then it goes back to the same point, or you require every time more force in order to make the shear slip. And this is very similar, not exactly the same, but very similar to what we discussed before about plasticity. You remember that in plasticity we said that we have some materials which are strain softening, and when they break they tend to form a fracture which is very localized, and when it forms also that energy gets released very quickly. And on some other cases we have these materials which are strain hardening, where always you require more stress in order to produce additional deformation. And in this case it's very similar. Even though sometimes you may have a shear failure that may not emit a lot of micro-seismicity, and if it doesn't emit a lot of micro-seismicity, then you're not going to be able to measure that on the surface. And even though if you could have quite a lot of stimulation, although you cannot measure it, it is there, and you may have a high production, cumulative production. So that's one explanation for this data. I'm telling you, this is real. These are our hypotheses. We're trying to understand what's going on. What about these other? You have a question, Robert?
Yes, I was going to ask if aseismic is the more stable of the conditions.
Yes.
Why is seismic more common in rocks?
No, I'm not saying it's more common.
Oh,
No, there are both types. Some people that study earthquake mechanics actually are very interested in measuring these friction coefficients for rocks, because this one leads to catastrophic earthquakes. This one, it leads to small earthquakes over time. So just to complete here, this is called velocity weakening, and this is called velocity strengthening. So very similar, remember, to our notation of strain hardening, strain softening. All right, so yeah.
What determines those two types?
This type,
Yeah.
it depends on the properties of the rock.
Or
Uh,
is it related with some surface roughness of the shear plane?
It could depend on surface roughness too, but then surface roughness, it would depend also on the type of rock. Probably, just to put some names in here, mostly brittle rocks like granite or igneous rocks will fall mostly in this category. Sedimentary rocks, shales, mud rocks will go more into this category. Sands, unconsolidated sands will go into this category. All right, so we were able to explain these cloud points. What about this one? In this one, we have a lot of screaming of the rock, but no production, no fluids that get out after that. What do you think would be a possible explanation of that?
There are a lot of reasons. For example, the fracture closure after the
Fracture closure, yes, so you're getting very close to that. Why the fractures wouldn't close?
disconnect.
Why? So we say this one was aseismic, and so fracture closure, right? But the objective sometimes is to keep the fractures open, right? How do you keep the fractures open? With propant. And if you have no propant, probably fractures close. So in many cases, if your propant is not efficient in propping those fractures, the fractures may close again, and even though probably you may have stimulated quite a bit, if you don't get any propant in it, here it says unpropped fractures, still your production is going to be very low. And this is especially the case when you have quite a bit of increase of effective stress. Remember when we talk about reservoir depletion that we say effective stress is increase? If your effective stress increase, and usually in fractures, the permeability of the fracture, the logarithm of permeability of the fracture is inversely proportional to the effective stress. So as you increase effective stress, your permeability goes down very quickly. And if you have no propant or propant embedment, then your production is going to fall very quickly. And that's actually a very big concern nowadays for unconventionals, because usually production rates may start high, but then they go down very quickly, much more quickly than with conventionals. So what do you do in order to solve this problem? For this one, we cannot do anything, okay? We just, you cannot change the properties of the rock. But what about for this one? What could you do in order to...
Propant to something that works better?
Okay, so one possible solution could be smaller propant, right? And actually that's something that is being applied nowadays to do, instead of use big propant, just use very small propant so it can reach further away to fractures. And I have an example here, it's not related with propant, but I think it's interesting, and I'm going to talk about this a little bit later on. So this is a piece of shale I found on a field trip I did with Professor Olson some time ago. So this is a shale. You can see the lamination over there, right? Come on, go focus. Okay. So you see laminations. So this is a vertical. This will be a vertical fracture. Likely you cannot see now next to my finger. This one used to be like this, but then one of my TAs broke it. So now you see it's broken over there. But before it used to be like this. It used to be stable like that. So here you have your fracture tip, and let's see, what can we do in order to improve this focusing? And let's see if I leave it in there. Okay, that's a little bit better. And if some of these fractures you see are very, very tiny, like microns, tens of microns, hundreds of microns width, and this one is open, right? If I were to close it, you see, you could barely see that. So some of the solutions nowadays is to pump what are called micro-propants, so very, very tiny propant that can help you prop some of those fractures. Especially sometimes if you have well, as in this case, imagine this fracture that opens like that and then turns into that location. In order to go through that twist, a big piece of propant will not go, and that's what is called propant screening in the fractures. So the smaller sometimes, the better. And there is one alternative solution for that. What could you do instead of injecting propants in order to keep fracture conductivity? Any suggestion? So we say micropropants. Another solution is to inject acids, to do acid etching of the fractures faces. So even though if they close after some time, you still may have channels that connect even though the fracture is closed. And both of these applications nowadays, I think there is a lot of field trials trying to make these two work in order to increase the productivity after the hydraulic fracture stimulation. All right. Any questions about this? Let me see what I have here in my notes. I don't have a lot more about this, so probably we can take a look a little bit more at this rock for a bit before I change, because I want to show something totally different in 10 minutes. All of the theory that we have seen is related to linear elastic fracture mechanics. And this applies very well for very stiff rocks and whenever you have a low permeability. And you can see, for example, in this case, this type of fracture, which is very thin, right? There is more or less well-defined fracture tip. If I show you here the other side of the fracture, so let me zoom a little bit more. You can see that that's your fracture face. Whenever you have changes of rock strength, you will expect also changes in the propagation direction of the rock. But it looks very flat, right? Let me turn it slightly. As you will expect with linear elastic fracture mechanics, you get planar fractures with a more or less well-defined tip. And as we were seeing in our equations, the width of the fracture is usually 100 to 1,000 times smaller than the length of the fracture. This particular rock, I took it from an outcrop. It was a shale, and this fracture very likely wasn't caused by fluids moving inside it, but it was caused by thermal cooling. And very likely also this one didn't happen overnight, but grew over a long time. One more additional topic that I like that you are aware of. We're not gonna go a lot into detail about this, but it's a phenomenon of subcritical fracture propagation. So far we have discussed fractures that grow up very quickly. As long as you go above a value of fracture intensity, this is the fracture intensity and this is the fracture toughness. As long as you go above that value, the fracture will propagate very, very quickly. But it turns out that sometimes you can have fracture propagation even at values smaller than the toughness value. In that case, it has been observed that as you approach the toughness value, your velocity goes very high, and you could say goes into infinity or goes into the velocity of sound for something that is opening very quickly. And if you have a value of intensity lower than fracture toughness, this one starts to deviate, and you can have a fracture velocity which is proportional to the fracture toughness. All type of fracture propagation which is below the fracture toughness is what is called subcritical fracture propagation. And this law usually is like this: the velocity is proportional to the some power of the fracture intensity. So the higher the intensity, the faster the velocity of the fracture propagation. And this phenomenon is very important for two things. One, for understanding those natural fractures that we said that sometimes they exist in formations. Before you do hydraulic fracturing, sometimes there are some pre-existing natural fractures. And understanding some of that, those patterns, is possible through this theory of subcritical fracture propagation. Professor Olson did a lot of work in this area. So if you check his papers, you will see how that can affect natural fractures. And also, when you do hydraulic fracturing, there might be some areas in which your value of intensity, it doesn't get to the value of toughness, but there might be some other areas in which it's below that value, but still you have hydraulic fracture or fracture propagation, but now this one is time dependent. So either for natural fractures or for hydraulic fracturing, understanding this phenomena of subcritical fracture propagation, it's very important. And in this case, we are talking about open mode fractures, but this theory is also the same for modes 2 and for modes 3. So remember, these are shear. This one is open mode. And this rock that I showed before very likely underwent subcritical fracture propagation with thermal stresses. And it took a lot of time for that fracture to form. Okay, so we are done with hydraulic fracturing parts of tight and stiff rocks. Hydraulic fracturing is not only done in unconventionals, but it's done in some other kind of materials too. You could also do hydraulic fracturing in sand. And those hydraulic fractures are going to look a lot different to what they look in well-cemented rocks. So let's talk about hydraulic fracturing in unconsolidated, so sediments. Before I throw any schematics or any interpretation of what you may expect, let me show some images that are going to justify what I'm going to say. So let's see if I can find this quickly. So I'm looking for a paper of a friend of mine. He was doing this work when he was a PhD student and I was in the same department. And he did experiments of hydraulic fracturing in sand. Probably that one. Yeah. Okay, let me see if these are the pictures. Okay, let me download the paper. So he did experiments in a big triaxial cell. So this is about 1 foot by 2 feet or so, in which inside he injects a very viscous fluid, and he creates fractures inside. That fluid hardens with time, and after he's done with the experiment, he just recovers all that hardened paste with the sand glued next to it, right? All the sand that didn't get into the fracture, it just falls, and you just recover what the fracture is. And this is one example. You see, this is the shape of a fluid-driven fracture in sand. It's a lot different than the ones that you have in rocks. Look at those sort of, I don't know how to call it, but bubbles. Let me go into full screen. Something else to notice, let's go into some other figures, is that the width of your fracture now, it's much bigger than the width on the fractures that you would expect in rocks, right? Compare this width to that length, is just a few times smaller, but this width is much bigger. In this type of sediments also, you have a lot of leak off. So although in this case you see this fluid, which is pure here inside the fracture, some of it also got inside the sand, and that's why that sand is cemented. Probably now I get back to your point, Min, about fracturing in highly permeable reservoirs. So sometimes you do that, but you do that to avoid other problems of sand production. Especially these applications for this type of fracturing, is what is called frac-pack completion, in which you inject very strong propants or sand next to the wellbore. So when you decrease the pressure, you increase effective stresses, you don't have the material failing next to your wellbore, and you don't produce that sand. But I hope that by looking at these images, you get an idea about how different, this is one of my favorites, how different these fractures look into these type of materials. And one more thing to look at, very interesting here, is look at those fingers. This one, but probably let's go over here, over there, here, there, and also many of those in here. What do you think is going on there? Why do we have this fluid getting into that particular direction? Notice that it's very consistent, right? Many of those at an angle from the direction of the fracture. Any ideas what's going on in here? What?
The shear
is shear failure, right? For the fractures that we were talking before, we talked all the time about open mode, except when we included natural fractures in it, and we said that there could be also some shear next to the main hydraulic fracture. Well, in here also you have shear in this type of material, and that makes a lot of sense, right? Because what is the tensile strength of sand?
0.
0, right? So can you apply linear elastic fracture mechanics to sand? No, right? So uncemented sediments tensile strength is 0, fracture toughness is actually not applicable or not defined. You cannot do that, because also linear elastic fracture mechanics does not work. This is a different material. Linear elastic fracture mechanics assume some cohesion, some bonds between the material. But in case of uncemented sediments, we do not have that. And because we do not have that, you cannot use this theory. There have been some people that, to a some more or less successful way, they use linear elastic fracture mechanics, but tune the properties KIC and Young modulus in order to get fat fractures and short fractures, but by putting fake values of these. So that's one possible solution. But with that theory, you will never capture those shear fingers that you saw in the images. And actually, I haven't seen a lot of work that actually can do this. And that's, to me, that's a very interesting area of research. But let's try to understand what's going on with this sand, how it fails. And in order to do that, we need to use some of the yield criteria that we have been using before. So a yield criterion for an uncemented sediment that captures better the physics of failure would be a criterion that has strain softening, strain hardening, and if you are somewhere over here before fracturing, when you do have the hydraulic fracture coming on, you may expect your effective stress to go down because you have leak off, you're decreasing the pore pressure, you're increasing the pore pressure, so leak off, increase the pore pressure. As you increase the pore pressure, let me write this logic down, increase the pore pressure, reduce the mean stress. If you apply stresses which are not symmetric respect to each other, so it's not an increase of, or a homogeneous decrease of the mean stress, anisotropic stress, what you're going to do is you're going to increase the deviatoric stress, and that will result in a path that goes in this direction, right? And probably at some point you might have failure, you may go into critical state line, and this is the way that your material is going to fall, to fail in these conditions. So let me do a schematic of this. This is your wellbore. In this case, now your fracture tends to be what this is if we put propant, okay? But let me not put propant right now. I'm trying to do a schematic of what you would expect for this fracture, how it would happen as you propagate a fluid-driven fracture. Remember that here you cannot have tensile failure, okay? So it's all shear failure. It's all shear failure, but it might concentrate into a small area, or what you would call a fracture, a wing, but at the same time, very likely you will have events of shear failure around the fracture. And as I was telling you before, sometimes this is done with injecting or using strong propants or bigger propant, so that after you are done with your completion, you can lower the reservoir pressure, and that fracture is going to resist and it's not going to fail. Sometimes you can even use this as a filter. So as the particles fail next to it, they get filtered by that frac-pack completion. Okay, I have let me complete this before I forget. So one application we say is to avoid sand production, and the other application is like any type of hydraulic fracture for completion of a single wellbore is to bypass the damaged zone. And when I mean damage, I refer to permeability, right? Sometimes you may have your drilling fluid that gets into the formation, and in order to get away from that, you can do a fracture. So I think that was mostly that I have to say about this. And the last thing I'd like to do, how are we doing with time? I want to talk about a little bit about freefem, knowing that, yeah, I think we have time. Yeah, knowing that you need to finish your homework by tomorrow. So imagine that you have a wellbore, and imagine that here we have well cemented rock, and here we have sand. If you were to do a hydraulic fracture in these two types of materials in the cemented rock, you will get a thin and long fracture. It looks like it closed over there. Shouldn't close. Let me fix this. In sand, you would rather get a short fracture, and you may have some deviations because of shear. So totally different materials. In this one, you have failure by tension. In this one, you have failure by shear. So I repeat, I think there is no good solution yet for this kind of problem. So if you come up with a solution, I think that will have a big impact. All right, guys, I think we're done with hydraulic fracturing. Let's talk a little bit about the homework. Have you guys finished the homework? So? No?
Any chance for an extension? I'm asking because I have an exam on Friday, so that's been kind of killing me.
So, well, we need to negotiate a little bit here, okay? Let me tell you what's going on.
This is the last homework assignment, yeah?
Well, that's what I want to say now. So, originally we had a homework due by tomorrow, but there is one more project I want you to work on. It's short, okay? It's short,
There was only 8.
but it's an important one, okay? It's an important one. So I can give you an extension then to Monday, but then you got to finish the other one by Wednesday. But okay, let me think.
Can you just give us both, or just can?
What?
Can you just give us the extra one now? And we can do
Yeah, I can do that. Yeah, that's what I was planning to do. But then, so both of those will be due sometime on Wednesday. Okay. So this is for your own good and for preparing for the exam, because I need to include this part of dynamics, and it's very simple. It's just computing Young moduli and velocities and linking those two. That's it. It's a very simple
And the exam
project.
The exam is Thursday the 6th.
Yeah, Thursday the 6th at this time, okay? But let's talk about freefem, okay? Because I know that some of you are struggling with freefem. So, I think I had uploaded this file. Okay, let's see if this works. Okay, this is the text file. So the first part is just a declaration of constants, okay? So here you may want to define the size of your domain. In this case, these are the sizes, this is the radius, elastic constants that you will need. And after that, you just calculate some other constants based on the other constants. And over here, these are your numerical values for your boundary conditions. It's just a declaration of constants, okay? So that's okay, that part? All right. The next part. The next part is the definition of geometry, okay? So each of these is a border. It's a border with a dummy variable t and an equation here in x and y. So for example, in this one, x size, that was a constant. You see, x size was 10. So in this case, you're telling that this is a line that goes from x equal to 5, and I varies from -5 to +5. So this is a line in x. So let's say this x and y. X is 5, it doesn't move, and y goes to -5 to +5. So this is just a line. And you do this by using this dummy variable t, okay, which is defined before. This is the range of variation of t. And all of those are more or less the same. And for example, in this case, your dummy variable is an angle, goes from 0 to 2 pi, and then x and y, always in 2D, are defined by a function where you, at least on one of those terms, you need to have that dummy variable. In your fracture problem, I strongly recommend that you do a half of a quarter domain, where, for example, in my case, I'm going to show you the solution of it. I have 6 boundaries. I have 1, I have 2, I have 3, 4, 5, 6. And in all of those, I impose no displacement, no displacement, no displacement, no displacement perpendicular to the line, and no displacement perpendicular to the line. And the only one that I leave without any prescribed displacement is this one, in which I put the pressure. Okay? But you will do that in this region. Make sure also that you change the size here so it's appropriate for the size of your fracture. In the problem, you have to simulate a fracture with a length which is equal to the fracture height, okay? And with the width or the pressure, you need to input the pressure such that it matches the width given in the assignment. In the paper it's 4 millimeters, but then I'm asking you to do it with 6, with 8, and with 10, I believe. I don't remember very well, but something like that. Okay. This part just shows the domain, okay? And each of these numbers tells how many lines you want in each of those. These are all straight lines, so it doesn't make too much sense to put 10. You could put 1, it will look the same. But for the well, yes, for the well it makes sense to have 40, so you make the subdivision of this circle into 40 straight lines, but this is just for showing purposes. For the mesh, it's very similar. This is how you create your mesh. And you say each of these boundaries, right, top, left, bottom, and well, are going to be composed by n triangles on that side, where n in my case here is 20. So in each of those boundaries, I'm telling the mesh I want at least 20 triangles. And in the well, I want 50 triangles all around that well. Also, in your problem over there, in boundaries 4, 5, and 6, increase the number of triangles so you have more meshing density closer to the fracture. And probably, I think in my case, for example, in boundary number 2, I have 10 elements. In number 4, probably I have 20. So it looks much denser on that side. And this is just plotting, showing what the mesh is. Here, this is the part that you don't have to touch. If you touch this, it's up to you, but if you don't touch it, it's going to work, okay? Here you define your final element spaces for displacement, for stress. And here you define your variables. And you're telling that U1, U2, V1, V2, the real displacement and the virtual displacement, those are displacement fields. And all these sigma xx, sigma yy, sigma xy, those are stress fields. Yes?
But in this question, we have like a delta SYY or delta SZZ, right? Because you asked us to add this one in the question. Is it plane strains?
Oh, okay. So what I'm going to ask you here is to use the principle of superposition. You solve this with freefem, and then you add that solution to your far field stresses. So because you knew your far field stresses, that's not going to change. You don't need any solver to do this, okay? So this is your, I'm telling you that this was HF, right? So this is the same as that one. This is going to be SZC, that's vertical, and this is going to be SXX. But just do it with no displacement. Just put the pressure on it. From here, you're going to have the additional stress because of the fracture. And from this, you already know what is the original state of the stress. So from here, from this solution, you're just going to get the additional stress. Again, this section, you don't really have to touch. This is just equations. And here is where you start making some changes in the boundary conditions. So in the boundary conditions, I'm asking you that for boundaries 1 and 3, you put no displacement on direction in the vertical direction. And for boundaries 2, 4, and 6, you do not put displacement on the horizontal direction. So all of those are going to be Dirichlet boundary conditions with prescribed displacement. The only boundary which is going to have a pressure is going to be, in this case, boundary number 5. In that boundary number 5, you need to use a Neumann boundary condition in which you have to multiply. You're going to have to use this one. In the area of the fracture, you multiply the pressure in the fracture times the vector normal to that line, and that's what is going to create the additional stress. What pressure in there? Well, you need to match the width which is prescribed in the homework. But actually, you can use for that, let me get over here. You can use for that the equation that we had in here. So you see here the width is proportional to the pressure for the plane strain assumption. If your code is working well, the pressure that you put in there is going to give you about the same width. Maybe slightly different, but it's going to be about the same. So use this equation to input the pressure in there. And after that, it's just plotting. And what I'm asking you in this problem is to export stresses at this point over here. At the center of the fracture, and export that for some length. You want to know what is the additional stress that you put in this direction, you multiply, you add these two, multiply by the Poisson ratio, that's going to give you the out-of-plane stress. And that's the one that we're interested in calculating, right? So in this example, we're assuming that we have a fracture which is like this, very long in this direction. This is our plane strain assumption. In the 3D, in the paper, they do it 3D. So the fracture starts like this, but then gets smaller and it has some certain length. Well, in our case, since we're calculating just in the middle of the fracture, we assume this is all plane strain and it's infinitely long, which is going to give, you know, some slightly different results with the paper, but it's not going to be too different.
So basically, we're just going to run the same model for both and plot basically the stress along the same line, then
Yes.
add the first case to the
Yes.
second one to account for the far field stresses.
Yes, correct.
And the first one is really giving us kind of delta S, which is what is in the
Yes.
what you're saying.
Yeah. And that's basically everything you have to do. Yes, Hamza.
We previously had the homework where we had to do like a fraction instead of like a fraction in
Yeah.
the middle of it.
Yeah.
Can we just use that?
You can use that one too. Yeah. It's just that it's exactly the same.
It's like just
It's exactly the same. Yes. Okay. So, any question about freefem that I could help you with? Remember, those are just the things that you need to modify. Oh, let me show you my solution. Let's see if I can connect to my computer. Yes.
So with
John.
the move mesh command, like, I got a lot of errors when I was like setting up the mesh that the triangles were reversed.
Okay, that's when you show the mesh.
That's when you show the mesh? Not when you
Some,
move
yeah,
it?
when you show the mesh,
Okay.
sometimes that or when you put some weird stresses, you might not be able to see what's going on in there. So probably just turn off the show mesh, show deform mesh line, and probably that will make it work. So okay, let me see.
That's a cause issues like that, yeah.
What's the name? Okay. So there is running. You see, this is my domain. Here are my boundaries: 1, 2, 3, 4, 5, and 6. Here I have my fracture. This is my mesh. Sometimes you have those problems of reversal of the triangles if the triangles do not look very much equilateral. If you have one of those or two of those lengths to be too much longer than the other one, that's going to cause some errors. So try to have your triangles that they have the sides to be more or less the same. So this is after you apply the pressure in it, and this is the value of displacement, number 1. This is the value of stress in this direction, stress in this direction, and the shear stress, out of plane stress, I also computed it here, you can also do that, and that's the 4 mesh, right? So after you do that, you come over here, and in this case, I guess, so let's take a look at my script. In my script, you see, I usually make drawings of here, so I can see a little bit better what's going on. This is the definition of my borders. Here's my mesh. Here are my elastic coefficients. Here are my values for stresses. I do not use all of them. And this is all the same as what you have in there. And here I have my boundary conditions. No displacements on the outside boundaries, and these are all commented except this one, which is the pressure in the fracture. And then after I do that, here is I calculate strains, stresses, and this is some other thing, calculate principal stresses, and I write a file out of here for a line in the middle of the domain. So I equal to 0, y equal to 0, x, that goes from where the fracture is to some length after the fracture. So what do I get after that? I get this, all this data that if you plot it, come on, what's going on? Okay. Prefer if you do this with MATLAB, okay? But I want to do it with Excel just to make it quicker. This is my line. That's my stress, if I remember correctly. Let's see. Yeah, that's XXX, and then let me and that's SYY. So you add those two, multiply times the Poisson ratio, and let's say Poisson ratio is 0.2. And here you will get the out-of-plane stress. Which is that one. So you add that to your far field stresses, and then you get the answer. But notice that the two stresses are changing, right? This stress is changing because now it has pressure from this side. So that one is going to increase too. And this one is changing too because the out-of-plane stress. You have to compare those two stresses after they have changed, both of them. All right, okay guys, I think with this we're going to end the lecture, and we're going to talk about wave velocity on Tuesday.